Hello, my name is Adar Amir, and I will be presenting our work titled DLACP, a deep learning-based framework for approximate complex event processing. This work was done under the supervision of Dr. Ilya Kolchinsky and Professor Assaf Schuster from the Technion. So first, let's talk about CP systems in general and how they work today. So a CP system receives data streams as input. These streams can come from various different sources, such as the web, warehouse data, mobile devices, etc. And these streams are processed by the CP engine, which employs an event processing rule base, which stores some predefined user-defined rules and extract meaningful patterns from the data. Usually, the engine extracts sets of events corresponding to a full match of these predefined rules or patterns. And these events can be used as, for example, alarms to the user that some occurrence of reported event happened. They can be used for analytics and reports. And the main point about CP systems is that they need to work in real time. They need to process the events in real time and alarm any kind of important occurrence in the data as fast as possible. Now, the main limitation on complex event processing is as events arrive to the systems via the stream, the engine needs to process and store each applicable event that may be composed with other events in the future to be extracted as a full match. This can be very wasteful because this accumulated data can end up being discarded in case not enough events arrive for it to be accumulated into full match. The evaluation time then therefore quickly becomes a performance bottleneck because it was shown in previous research that the number of partial matches maintained may be exponential in the number of applicable events. And this problem, unfortunately, is deeply magnified when either the window or parallel length is enlarged, which instigates severe scalability issues. Now, this is the main problem right now today with CP, and there are various different types of optimization to it, and our optimization is based on pre-shading events that do not participate in full matches. So eventually, at the end of the day, what we care about are only the full matches and not the accumulated partial matches. So if we had a way of knowing in advance what events in the stream do not participate in full matches, we can simply drop them and have the complex event processing engine process only important events that participate in full matches. Now, our optimization is based on employing deep learning for filtering out these unimportant events and retaining only the important ones. Now, on the one hand, deep learning models are good at detecting patterns. We've seen that in image detection, for example. So logically, they should also be good at detecting events participating in full matches. And one of the strong points about them is that they are not affected by most pattern and data properties. They are affected, but not as severely as exact CP, which is the typical CPs today, because it does not need to accumulate events as they arrive. However, one of the main problems is that these models are inept at actually partitioning these detected events into unique full matches. So they are good at detecting the important events, but the main task imposed on CP is actually to partition the events into sets of full matches. So our system, basically what we decided to do is to integrate neural network pattern detection capabilities with complex event processing engine matching capabilities. And our system, as far as we know, is the first one integrating these two in order to perform a complete complex event processing and match extraction. Now, former research employed deep learning for example, automation of rule learning or to predict future complex events. So research employing deep learning in CP is not very extensive until this point. So let's start talking about our system in general. So our system is titled DLACP. We assume that data arrives to the system from a single source or is merged into one. The system receives a single complex pattern which we need to detect and extract full matches for, but this can also be readily extended to the multi-pattern case with modified labeling. And we also assume that the pattern is embedded with a count window size of double. We've also shown in later experiments how the system can handle time-based evaluation of windows, but the main evaluation method we use here is count-based evaluation. So the first part of our system is the DNN input assembler. The data stream can be very large, and we need to decide on a way in which we partition it in order to be later to be handled as input to the inner neural networks, because LSTM networks require either a fixed input size or at least some kind of maximum input size. So what we did is we partitioned the input streams into chunks of 2 W events, where at each step we skip W events. So each time we look at 2 W events and skip W events, which W, of course, is the embedded count window size of the pattern. And the reason we decided these values is because preliminary experience we've done on our system shown that these values attain a good balance between the match quality and throughput gain, which are the main metrics we've used to evaluate our system, over exact CP, which is the typical CP used today. So after chunking the input stream, each chunk is being used as input to the network, which is the DNN-based filter. DNN-based filter basically employs the network which we've used a bidirectional LSTM-based networks and mark events participating in a full match within each such input window. And we filter out the unmarked events. That means that only the marked events are relayed forward for CP evaluation later on. Now we've actually implemented 2 variations of this network on different granularities, and our system can employ either one. So the first kind of network is the DNN-based filter called the event network, in this case, all the events are being relayed through a bidirectional LSTM network, and each event at the end is giving a label of either 1 or 0, where 1 meaning this is an important event that participates in a full match, and 0 means that it can be discarded. And the second kind of network is the window network, which is basically it receives each event in the window, but on each window receives only one label, either 1 or 0, where 1 means that there is at least one full match inside the window, and 0 means that it doesn't even have one full match. So we can see that these networks have different granularities in their approach to the data, and each has their strengths and weaknesses. For example, this network is usually more accurate because we treat the window as a whole when we relate forward to CP. However, this network also retains a lot of unnecessary events, can retain a lot of unnecessary events when relating to CP, so the CP extraction time can be a bit slower. Now, during training, we've used the F1 score to evaluate our models, which is using this formula to combine between the precision and recall. And this serves as an indicator on the one hand, our system should achieve high throughput. And on the second hand, enough amount of emitted matches are being outputted from our system when we evaluate newly seen streams. Because at the end of the day, we want our system to not only be as accurate as possible, but also be as fast as possible. So this score attains a good balance between these two. The last part is the CP extractor, which basically after filtering out the stream, the filter stream is being relayed to a typical complex event processing engine, which extracts the pattern into different window matches. Now, because complex event processing engine cannot make any faults, it is 100% accurate. We do not have false positive matches, meaning all our matches are correct, but we can, of course, miss some matches in case the network filtered out events wrongfully. However, in the case of negation, we can have false positive because if our network wrongfully filtered out some events, then the complex event processing engine, when it works on the filter stream, can accidentally output a false positive match still in the case of negation. Now, in the experimental section, we tested our system on a wide variety of patterns. They demonstrated different values of important parameters, such as the amount of partial and full matches, pattern length, etc. And we tested our system on a real-world stock data set taken from NASDAQ and also on synthetic data. We measured both the throughput gain of our system over exact CP and match recall or F1 score, where any original full match our system lost counts as a false negative. And unless stated otherwise, in all experiments, we attained a very high recall or F1 scores, which were 0.95 and above. And the window network compared to the event network achieved a slightly better recall. So the first experiments, we've tried to assess the impact of the amount of partial and full matches. So for example, in this experiment, we've tested on patterns with different amount of partial matches, where Q3A had the largest amount of partial matches. And in this case, our throughput gain was the largest. In this test, for example, in the C graph, we tested on different amount of full matches, where Q1A, where alpha equals to 0.76, we had the smallest amount of full matches. So these experiments indicate that the more partial matches we have for the pattern in the data, combined with the with a lesser amount of full matches, indicates our system will work better and better over exact CP. Next, we tested the impact of the pattern operator length nesting. So for example, on the B graph, we've tested the performance on a clean closure pattern on different nesting levels. And we see that actually when J equals 5, this is the largest nesting level and the lengthiest pattern. We see that our system works the best. We have a much larger throughput gain. And also in different patterns, we see that usually the more complex the pattern is, the larger the throughput gain is. We also had an experiment where we compared separate evaluation of patterns versus evaluating their disjunction pattern. So for example, when we tested each of these patterns individually, we received these throughput gains, but when we evaluated on one pattern, which was the disjunction pattern between these two, we achieved a throughput gain that doesn't fall a lot off over the higher throughput gain. So this means that in case it might be better, more efficient to actually evaluate two patterns combined instead of each one separately. Next, we've tried to assess on the cases where our system is wrong, where we emit false negatives, we try to assess why does this happen. So we've taken some showcase pattern and we've seen an interesting phenomenon in which when we try to separate the matches that we didn't manage to detect, the false positive, and patterns that our system did manage to detect, we've seen that on patterns that we didn't manage to detect, the variance of the volume attribute was a lot higher and went all over the place. So this indicates basically that we can already determine in advance on a lot of cases where our system will be a bit better and when will it be a bit worse, and it will and this has a very strong connection to the variance in the feature embedded in the pattern we're seeking. Next, we try to assess the impact of the amount of training data and training length on our system. One of the main disadvantages of our system is that we employ a neural network which needs training. Neural networks sometimes need a lot of time training and a lot of data. But on this experience, on another showcase pattern, we've seen that even with a relatively smaller number of epochs, training epochs, or a smaller number of data percentage used, the throughput gain does not vary widely, while the false negative percent reaches a plateau relatively early in terms of data percentage used and epochs used. This means that we do not actually have to fully train using all our data and all of our training time to reach a very good results with our system. Another test we did is we have, as I said before, optimized exact CP processing by pre-training events, but there are also other methods, state-of-the-art methods used for exact CP optimizations. These methods, of course, do not use deep learning. So we've compared our system against theirs, and in all the patterns we've tested, the sequence, conjunction, and disjunction, we've seen that our system achieves a much higher throughput gain. Of course, the main difference is that these other optimization methods are 100% accurate and our isn't, because we employ a neural network, but our recall was still very high for these patterns, 0.81, 0.94, and 0.94. So we achieve a much larger throughput gain without losing a lot of matches. Another test we did was testing the impact of pattern length, window size, and number of bidirectional LSTM layers. We've seen that the larger the pattern is and the larger the window length is, the better our system performs. For example, if we have a 350 window size and length X, our system is 1,000 times faster than exact CP. However, this comes at a price of recall deterioration, because the more complex the pattern is, the more trouble our network has in detecting the pattern, and our recall drops off a bit. But this also can be addressed by extending the number of layers used in our network. We see that the more layers we use in our network, the better the recall becomes, because the network can better capture the inherent underlying pattern. But this also comes at the price of throughput gain, because the larger the network is, the more time it takes to process events. And finally, our main window evaluation that we use is count-based evaluation, but in reality, there's also time-based evaluation, where windows can be comprised of different number of events. So what we did to simulate that is basically use different value of maximum window size. For example, if maximum window size is 250, it means we use a window with different varying number of events, but the maximum one was always 250. So we've used these different varying window size and padded some of them to the maximum amount, and then employed our network, our system, and we've seen that still in these cases, we achieve a much larger throughput gain over exact CP. So this simulation suggests that even on time-based evaluation, our system should still achieve much better results. Thank you for listening. If you have any more questions, feel free to contact me. Thank you.